Welcome to this explainer. Today, we're going to break down the massive engineering challenge of keeping the internet's brain cool. Every time you stream a movie, send an email, or prompt an AI, you are relying on this invisible infrastructure that runs incredibly hot. So today, we're looking at the absolute unsung heroes of our digital age, data center chillers. So what is the single most important machine keeping the internet from melting down? Let's dive right in. Behind every single digital action you take, there is a piece of hardware generating an unbelievable amount of heat. If you've ever felt your laptop get uncomfortably hot on your lap, just imagine millions of those processors packed into a single warehouse, running nonstop. Without a highly specialized industrial-scale cooling system, the physical infrastructure of the internet would literally melt down in minutes. No joke. Here's our roadmap for today's explainer. First, the data center heat problem. Second, water versus air cooling. Third, compressors, which are the chiller's heart. Fourth, eco-friendly cooling trends. And fifth, how to choose a chiller. Let's get to it. All right, Section 1, the data center heat problem. Let's start by establishing the sheer scale of the problem we're dealing with. It is absolutely crucial to understand that cooling a data center is nothing like air conditioning your house or an office building. Unlike a typical office that empties out and powers down at night, a data center is like a high-performance athlete that literally never stops running. It releases massive amounts of heat from its IT equipment 24/7, 365 days a year. Because of this, it requires huge, high-reliability chillers that go way beyond standard AC. Moving on to Section 2, water versus air cooling. To solve this monumental heat problem, engineers basically have to choose between two main cooling methods, water or air. But before we compare those, we really need to understand a vital metric called COP, or the coefficient of performance. Maximizing this efficiency metric is the ultimate goal for any facility operator out there. Simply put, a higher COP means the chiller is doing a much better job of removing heat while using way less electricity. And when you're operating at the scale of a hyperscale data center, even a tiny fractional improvement in your COP can save millions of dollars in energy costs. So, engineers face a fundamental choice. Do you harness the supreme efficiency of water or the logistical simplicity of air? Water-cooled systems use cooling water to chill the refrigerant, and this gives them the absolute highest levels of energy efficiency, or COP. Plus, they're perfect for large-capacity facilities and are really stable against outside weather changes. Air-cooled systems, on the flip side, are completely waterless. They have a simple structure, they're incredibly fast to install, and they are significantly easier to maintain. But, neither option is perfect. It's really a game of trade-offs. Water cooling consumes massive water resources, requires cooling towers, complex piping, and intense management to prevent risks like Legionella bacteria. Air cooling, meanwhile, requires a massive land footprint for all those external fans. Plus, it has a lower base efficiency that drops pretty sharply during the hot summer months. Okay, Section 3, compressors, the chiller's heart. Now that we understand how the heat is displaced into either water or air, let's look deeper at the mechanical heart of the chiller, the part that actually compresses the refrigerant and pumps the system. Engineers generally choose between two types. First, the centrifugal, or turbo compressor. This absolute beast uses a spinning impeller to handle huge capacities. We're talking 500 to over 3,000 refrigeration tons in a single unit. That makes it the standard for hyperscale water-cooled operations. Then you have the screw compressor. It uses meshing rotors, is highly durable, and handles fluctuating loads like an absolute champ. That makes it the standard for mid to large air-cooled centers. Next up, Section 4, eco-friendly cooling trends. These base technologies we've just discussed, they are evolving at a blistering pace right now, thanks to the massive surge in AI and some very strict carbon neutrality goals. To hit these goals, data centers are totally obsessed with a metric called PUE, or power usage effectiveness. To lower their PUE, data centers can't just rely on standard chillers anymore. They desperately need revolutionary upgrades. So, the crucial innovation here is a feature called free cooling. Imagine it's winter, or even just a crisp autumn day. Instead of firing up that power-hungry compressor we just talked about, free cooling allows the system to use cold outside air to chill the water directly, without running the compressor at all. This dramatically lowers the PUE and completely avoids water waste, making large air-cooled chillers with this feature the absolute hottest new trend in the industry right now. And it gets even cooler. Engineers have taken the compressor and given it a sci-fi upgrade with the magnetic bearing or oil-free chiller. They've started literally floating the compressor axis using magnetic levitation. This completely eliminates physical friction and the need for lubricating oil. Why does that matter? Well, it delivers shockingly high efficiency, especially when the data center isn't running at full load, which is most of the time, since workloads are constantly fluctuating. Alongside these incredible hardware upgrades, the actual chemical blood of the system is changing. To meet strict environmental regulations like the Kigali Amendment, the industry is rapidly phasing out old HFC refrigerants like R134A. In their place, there's a rapid adoption of low global warming potential, or low GWP, HFO refrigerants. We're talking about new standards like R1233ZDE, R1234Z, and R1513A. And these aren't just suggestions. They are now actively mandated by global tech giants like Microsoft and Google. All right, our final section, Section 5, how to choose a chiller. With all these options out there, how does a facility actually choose? Well, operators have to meet 3 mission-critical requirements. First, fast restart. If the power fails, the chiller must recover and resume cooling within tens of seconds after the generator kicks in. Second, VFD inverters. The compressor must adjust its frequency dynamically to match the constantly fluctuating heat loads of AI servers. And third, N+R redundancy. You absolutely must have precise sequencing and backup units, like N+1 or 2N configurations, to ensure zero downtime. Because honestly, even one single second of cooling failure can take an entire network offline. As we wrap up this explainer, there is a fascinating paradox happening right now, driven entirely by the high-density nature of modern AI. You see, hotter running high-density AI servers are completely changing the baseline rules of cooling efficiency. Because AI servers run so hot, the target temperature for the chilled water they need has actually shifted. Historically, chillers had to output water at a chilly 7 to 12 degrees Celsius. But today, for these new setups, that requirement has increased to 15 or even 22 degrees Celsius and beyond. And here is the paradox. Higher chilled water supply temperatures actually reduce compressor work. It significantly increases free cooling operating hours, which maximizes the utility of air-cooled free cooling chillers. Basically, hotter servers make cooling more efficient because facilities can just turn off their compressors and rely on outside air for much longer portions of the year. It's a real game changer. Which brings us to the end. It leaves us with a critical thought to ponder. We've engineered magnetic bearings and harnessed freezing winter air to keep our servers running. But as our digital brains get hotter and demand higher baseline operating temperatures, will the physical limits of our cooling infrastructure eventually cap the growth of AI? Are we hurtling towards an invisible thermal ceiling? It's definitely something to think about the next time you type a prompt. Thanks for joining this explainer, and we'll catch you next time.